number 5 of the form. Oh yeah, thank you. I should have reminded you to record this. Yeah, so welcome to session number 5, Logics and Theory. We're looking forward to 4 very interesting talks, and our first speaker is Gal Amram. I hope I pronounced this correctly, who received his PhD from the Ben Gurion University in 2018 and is now a postdoc at the Tel Aviv University, if I'm informed correctly. And I'm very interested to hear his talk. So the stage is yours.
Yeah, so I will use the recording. Sorry for that. Also due to say a typical November sore throat. So here it is.
The volume is very low now. We cannot really hear it.
It's low.
Maybe you are not share your sound of your computer, only share the screen. So you have to click the button of the sharing screen, and in the bottom left corner
If you don't want to present this live, maybe we can also use the pre-recorded video. Do we have one?
You can't hear? Is there a problem?
Yes,
maybe it's better to play the video from my part.
Okay, so I stop sharing.
Yeah,
Okay.
because it was so low, it was even with my very good earphones, I could not understand it. So
sorry for that.
So we are waiting now to get the pre-recorded video running, and here it is.
Can you see the screen?
Yes, we can see the screen.
Okay.
Hello everyone, my name is Gal and I will speak about efficient algorithms for omega regular energy games. This is joint work with Shahar Maoz or Pistiner and Jan Oliver Ringert. To speak about energy games, first of all we need a brief overview about reactive synthesis. A reactive system is a system that reacts to actions that come from its environment. Some examples are a vending machine, a server that reacts to client requests, a lane assist, and an auto-lane system. And reactive synthesis is an automatic procedure that constructs a reactive system from its temporal specification. Let's see some example. This is a variant of the obstacle evasion problem, the well-studied obstacle evasion problem. And what we have here is a moving obstacle, which is the environment, and a robot, which is the system that we want to synthesize. Now, in each round, the environment, the obstacle moves first, and it can move up to one cell at any direction it chooses. And then the robot, which is faster, can move up to 2 cells in each direction it wants. And in addition, if the robot ever gets caught by the obstacle, then it is stuck. It has no further legal output to produce. Okay. In addition to this conducting, a specification also comes with a winning condition. Some condition that the system must make sure will be satisfied. Here we have some very useful winning conditions. Safety. Safety means just avoiding a deadlock. We have to make sure we always have a legal output for the input from the environment. In our case, safety just means that we must evade the obstacle for eternity. Reachability. Reachability means that there is some goal we need to satisfy once. For example, the robot must reach one of the grid corners. Bookie means that there is some goal we need to satisfy infinitely often. For example, visit infinitely often a grid corner. Generalized bookie means that there are some goals and each must be satisfied infinitely often. For example, the robot must reach every grid corner infinitely often. And finally, GR1. GR1 means if some assumptions are satisfied infinitely often, then the system must satisfy some goals infinitely often. For example, if the obstacle reaches every corner infinitely often, then the robot must do so as well. In this talk, I will focus on the realizability problem, not on the synthesis problem, meaning that we want to find all initial states from which the system can win. We have a winning strategy. In our case, meaning finding all initial locations for the obstacle in the robot such that the robot can win with respect to the winning condition we choose. Now, mu calculus is a fixed point logic, very useful to solve realizability. You don't need to know what is mu calculus for this talk. I just want to tell you that, first, the semantics of a mu calculus formula is a set of states, and mu calculus is computable. In this table, we have mu calculus formulas that match those winning conditions. You don't need to know or to understand these formulas, you just need to know that someone wrote these formulas and proved they are correct, and now we can use them. These formulas give us an algorithm to solve the realizability of specifications with those winning conditions, and this is the time complexities we get. Okay, so we have these formulas and we can use them to solve realizability. Okay, now let's add the energy to the picture. We equip the system with a battery of capacity C, and this time, steps of the system may consume or regain energy from the battery. For example, let's decide that each step of the robot consumes one energy unit from the battery, but we have a charger that can fully charge the battery, say, in a single step. Reactive synthesis with energy is more complicated because we still must fulfill the winning condition, but now we have to do it without exhausting the battery, without running out of energy. So actually, there is a very simple solution to reactive synthesis with energy. What we can do is to add variables to the specification, add loxy variables, to model, to encode the energy level. And the cost of this reduction, if you have a solver that solves that matches some winning condition at once in time order of Fn, then because we add variables to the specification, we get a solver that runs in time order of Fcn. Because the problem is more complicated, we consider this cost reasonable. An advantage of this approach is that it allows the reuse of existing algorithms. For example, let's assume that you have some, say, bookie solver. You can solve realizability for specifications with bookie winning conditions. Now you apply this reduction, you add variables, you apply your tool, and what you get is a solver for bookie games with energy. This is great, but unfortunately it turns out that this approach performs very bad, and I will try to explain why later. And our goal is somehow to achieve everything. We want a technique to solve energy games with the same cost that allows you to use existing algorithms, but with much better performance. And our solution is to propose the energy mu calculus logic. The energy mu calculus logic is the same syntax just like mu calculus, but its semantics is different. In mu calculus, the semantics is a set of states. And the goal, if you write correct formulas, is that a state S will belong to W if and only if the system can win from S. And in energy mu calculus, the semantics is a function, an energy function, a function that maps states to energy levels. And the goal is as follows. If we write a correct formula, we want f of S to be the minimum CO, the minimum energy level, such that if we start from S with CO energy units, we can win. So this is the minimal initial credit sufficient for winning from S. But what is the main idea behind energy mu calculus? And if you get this slide, you understand energy mu calculus, even without knowing what is mu calculus. The crux is to define the predecessor operator of this circle diamond operator. So let's see. In mu calculus, when you have a set of states W, the predecessor of W is all states for which the system can jump into W. It can reach W in a single step. So the predecessor of W is just one step reachability. But what is the predecessor of a function? When you have a function f, its predecessor is another function that will map S to the minimal CO such that if we are at state S with CO energy units in our battery, then we can reach some state T in a single step with at least f of t energy units. So this is just like a one-step reachability into F. Reach in one step the energy level that F assigns to some state T. Okay, having said that, we have the correct definition for the predecessor operator, and hence the following theorem holds. If you have a mu calculus formula psi that solves games with winning condition phi, no matter what is phi, it can be bookie GR1 reachability, then you can take the same formula, the same psi, and with the energy mu calculus semantics, you get a formula that solves energy games with the same winning condition. And this is our solution. We take the formulas we saw in slide 6 in the table, and we just interpret them as energy mu calculus formulas with the energy mu calculus semantics. The cost, because we deal with functions and not with set of states, is that if your solver runs in time order of fn, now it runs in time order of fcn, which again it is reasonable. An advantage of this approach is that it also allows to use existing algorithms, right? Because of this theorem. If you have a solver that uses some mu calculus formula, you take the same formula and you can solve energy games. And it turns out that this approach performs very well. Now, I can show you the numbers. But before that, I want to try and explain why. Why our solution works and the naive encoding not that much. Let's see. Let's assume we want to say the system can win from S if it has at least CO energy units in its battery. With energy mu calculus, we just write f of S is CO. But with naive encoding, we need to write S, the state is S, and the energy level is CO, or CO plus 1, or CO plus 2, and so on. Therefore, on the left side, we have a relatively small representation which is independent of the battery capacity C. And this means when we will try to compute the semantics of the mu calculus formula, the energy mu calculus formula, the operations we are going to perform over our data structures are going to be relatively cheap. And it doesn't matter if C is small or large. You don't see C here in this formula. But with naive encoding, we have a large representation that is highly dependent on the capacity C, which means when we are going to try and compute the semantics of the formula, the operations we are going to perform over our data structures are going to be very expensive, especially when we enlarge the capacity C. Okay, let's see some numbers. So we implemented both methods, naive encoding and energy mu calculus, into Spectra. Spectra is the GR1 synthesizer. And we took two problems, obstacle elevation, the one I spoke about, and an arbiter, some problem from SynthComp 2020, the synthesis competition. And we created specifications with those winning conditions, safety, reachability, bookie, generalized bookie, GR1, and with those energy capacities, 100 to 1 million. For each specification, we checked realizability 70 times, each time with some sampled energy rates, and we report the median running time. So let's see. We have here obstacle elevation and arbiter, and we have the winning conditions, safety to GR1. We have the capacity, the battery capacity, from 100 to 1 million, and the method we applied, naive encoding and energy mu calculus. For example, when we took the specification obstacle elevation, winning condition, generalized bookie, and capacity 100, With naive encoding, we checked realizability in 17 seconds, and with energy mu calculus in 10 seconds. But when we increased the capacity into 10 to the 5, naive encoding took about 2.5 minutes, and the energy mu calculus roughly the same, 8.3 seconds. But when capacity was 1 million, naive encoding reaches the timeout, 10 minutes timeout, and the energy mu calculus is not really affected. We get 7.8 seconds, roughly the same. In all our experiment, we see that energy mu calculus is not affected by the battery capacity, and the naive encoding becomes infeasible. Okay, some conclusions. So energy mu calculus surely outperforms naive encoding. It is scalable and it is agnostic to the battery capacity. And also we see that naive encoding is highly affected by increasing the capacity, and it quickly becomes infeasible. Therefore, in summary, energy mu calculus is an efficient and scalable technique to solve omega regular energy games, and it allows reusing existing algorithms, mu calculus-based algorithms. A few future directions. We spoke about realizability. We want to implement also a synthesis to synthesize winning strategy. I will mention that it is straightforward, at least for the winning conditions I spoke about. As it is done without energy, roughly the same. Some other directions to deal with unrealizability if you have an unrealizable specification, and to compute counter strategies for unrealizable specifications. And also, today we still have no lower bounds over this problem, synthesizing omega regular energy games. So this was efficient algorithms for omega regular energy games. Thank you very much.
Thank you very much for this very nice talk. And I think we have a few minutes for questions. Or are there any questions from the audience? I'm not sure whether this was a question. I will just make a start and ask one question. In your talk, you showed at this reachability property where we were interested whether the system can reach some state with at least some given energy level. Can we also do it the other way around to say we have at most some energy level, or did I confuse something there?
I'm not sure I understand the question, but you have you need to set a bound on the capacity of the battery.
Okay.
Answer the question.
So you basically make sure that your battery is not running too low.
Not running too high. Say.
Not running too high. Okay,
yeah,
then
you have a bound on the capacity, but you're not allowed to run out of energy. You cannot have a negative energy level.
Yeah. Okay. So what you do there is modeling that the energy does not run too low. And when I looked at your paper, it seemed like the environment you model with this robot example is deterministic. Is that correct?
Say that it is deterministic.
And if yes, and can you also cope with non-deterministic environments?
Of course we can. It's just we added some assumption that the obstacle chases the robot, because otherwise it is unrealizable. But it's just a technical detail.
Yeah, which is actually pretty funny. I like that about the example. Okay, thank you very much. So thanks again for this nice talk. I guess there will also be a chance to talk with you about this in the coffee break after this session. So I'd like to move on to the next speaker, which should be Kushrai Matnami.